So, good morning, everyone. Today we will start with the next topic, Laplace Transform. Okay. So, till now we have discussed about various transforms, where we have discussed about Fourier series, Fourier Transform, and these two transforms they were specially meant for the continuous time signal. Okay. Subsequently, we have also discussed discrete Fourier series, discrete time Fourier transform, discrete Fourier transform, and how to implement the discrete Fourier transform using the first Fourier transform. Okay. And these three, that is the discrete Fourier series, discrete time Fourier transform, and discrete Fourier transform, they were used for the analyzing of the discrete time signals and systems. This we have discussed. Now, in general, if you try to see what kind of signals can be analyzed using all these transforms, whatever we have discussed till our last class. So, these transforms they can analyze energy signals and power signals efficiently. Obviously, there will be some differences. So, they would be analyzing either energy signals or power signals or both the stuffs equally. Okay. Now, they have certain disadvantages. What are the disadvantages? We saw that there are certain type of signals which are neither energy signal nor they are power signals. Okay. Under this condition, the aforesaid transforms it fails. If you have to analyze neither energy nor power signals, or even the or in other terms, you can say the signals which are going out of bound or which are neither growing nor decaying. Okay, so if you have to analyze many of these signals over here, especially if we can categorize those in the category of this neither energy nor power signal, then those signals cannot be analyzed using these aforesaid signals. Okay, so this is what I have shown you in on the right hand side. We started with Fourier series, which was meant for the power signals, that means the sinusoidal signals. Okay, when we went to the Fourier transform, we saw that Fourier transform it can be used for power signals. Also, it can be used for this sorry periodic signals. This is not power signal. These are periodic signal. Periodic signal. When we went to Fourier transform, we could analyze both periodic signal and non-periodic signal. Okay. So again, when we talk about the Fourier transform, we saw it can analyze energy signals and it can analyze power signals. Okay. However, the problem over here, as I just now told you, that they were not able to analyze non-energy, neither energy nor power signals. Okay, so we had to generalize the Fourier transform to get another transform which is regarded as Laplace transform. So in the Fourier transform, from where did we get it? We got the Fourier transform by the generalization of the Fourier series. Now, what we are telling? We are telling that we will be getting Laplace transform by generalizing the Fourier transform. Okay. So, in gist, if you see the mother of all transforms, you can tell us that Fourier series is the mother of all transforms. Okay, from Fourier series by generalization we get into Fourier transform. Then again, by the further generalization of the Fourier transform, we get into the Laplace transform. Okay. You need to keep in mind that Fourier transform till date, it is one of the robust transforms, and it is very commonly used in many fields. Say for example, we use in the field of geology. Okay, we can use it in the field of medicine. We can use it in the field of computer science. We can use it in the field of, say, electronics and communication. We can use it in the field of electronics and instrumentation. We can use it in the field of mechanical engineering, and so on. Okay. So if you see the versatility of the Fourier transform in analyzing different types of signals, so it is having a wide applications. And why this wide application? Because it is very robust. But as we discussed a few moments back, there is one problem with this, that it will not be able to analyze neither energy nor power signals. This is one of the disadvantages of the Fourier transform, and that is why we need this kind of generalized system or transform like the Laplace transform to analyze a wider variety of the signals and the systems. Okay, so while we will be discussing the separate stuffs over here, we are seeing that there would be two types of signals which we will be associating. The first one is the analog frequency. Analog frequency, it is very much, it would be what you call, we can use it interchangeably with the continuous time signal, even though we have seen that analog signals, they are having a separate identity, whereas digital frequency, they are having a separate identity. However, still, if you see, when we say analog frequency, we basically means with the continuous time frequency, what we get, that we regard it as the analog frequency. So usually the analog frequency, it would be marked with this omega. Okay, it would be marked with this omega. So these are the generalizations which we will be using it throughout the next part of the lectures, when we get into the digital filter designing. So keep this in mind. So this is important. Analog frequency, they will be represented with omega, which looks like ohm, and then the digital frequency will be represented by this omega, which looks like w. Okay, now when we are working in the continuous time domain, ft, if you perform ft, we get to the frequency domain. So this is capital X omega, this omega is, which is represented by the ohm. Okay, and again, when we apply the inverse Fourier transform, we get to the xt. Similarly, if you talk about xn, where we apply either the dtft or dft, if we are applying dft, we get x of omega, the omega denoted by w, and if we use dtft, we get x of omega, omega represented by the ohm sign. Okay, and again, if we apply either the idtft or the idft, we get back to the xn domain. So these things should be clear in your mind. Okay. Now the next thing is that when we talk about the Laplace transform, Laplace transform, it deals with the continuous time signals. It deals with the continuous time signals. Why? As I told you, when I am talking about the Fourier transform and I am talking about the generalization of the Fourier transform into the Laplace transform, that means what? Fourier transform we discussed it in the case of continuous time signals. Fourier transform we discussed it with the on this continuous time signal. Okay, are you getting my point? Now that means when we are deriving Fourier transform to get the Laplace transform, this Laplace transform it is also meant for continuous time signal. Laplace transform it is also meant for continuous time signal. Okay, so when we talk about continuous time signals, they are usually represented with differential equations. Okay, so the Laplace transform it is used for the analysis of the continuous time signals and systems. Okay, now these continuous time signals and systems they would be represented with differential equations. Say for example, we give the example dy by dx. Okay, now our course is on biomedical signal processing, and what we discussed, we will mainly be discussing about the digital signal processing for biomedical applications. Okay, so if you see our previous this transforms, we had Fourier transform which was working in the continuous time domain, and then we also had discrete Fourier transform which was working in the discrete time domain and also the digital domain. Okay, so because digital signals they are also discrete time signals, right? So similarly, when we are analyzing various signals and systems, we should be having two types of transforms. The first type of transform is the Laplace transform, which is acting in the continuous time domain, and there should be another transform which should be active for the discrete time Fourier transform. No, sorry, discrete time signals or discrete time domain, right? So the contemporary of the Laplace transform for the discrete time systems is the Z transform, in which we are quite interested. Okay, so post the mid-sem we will be discussing about these things uh, in depth. Okay, so we are having this Z transform. Now this Z transform they are represented with the difference equations. They are represented with the difference equations. So just a few moments back, I told you the differential equation, say for example, they will be having this dy by dx denominations. Now, if I have to convert it into, or if I say, if I want to make it suitable for the discrete time, this processing, then this dy by dx, it should be replaced with yn minus yn minus 1 divided by xn minus x minus 1. So if you see dy by dx, it was in the continuous time domain, and when I am representing the same thing over here, what is that? This is nothing but n yn minus yn minus 1. So you are having delta y divided by delta x, right? So this dy by dx and delta y and delta x they are analogous, and however this delta y by delta x it is nothing but it can be applicable for the discrete time signals and system. So you can see just by doing certain manipulations we are able to go from the continuous time domain to the this discrete time domain quite easily. So we will be understanding this while we'll be doing the mathematics for the this what you call this filter designing and all this stuff. Okay. Now I told you that Fourier transform, it cannot analyze all the system or signals and systems. So what does that mean? This means that the Fourier transform, it exists only for a restricted class of signals. Okay, only for a restricted class of signals. Therefore, it cannot be used to analyze signals that are growing exponentially. Okay, which are growing exponentially. I told you, any signals which are growing out of bound, they cannot be analyzed using the Fourier transform, and hence there is a need for another transform which will be able to handle this kind of signals like the growing exponential signals, right? So due to this reason, suppose if you have to analyze a system, suppose say for example, leave the systems, suppose I want to analyze, say, Rumin. What I need to do, I need to analyze his behavior on a day-to-day basis. What is his behavior basically? His behavior is the inherent property or the inherent signals which he is generating in front of me, right? So I am analyzing that to understand what is the quality of roaming, right? The same thing happens over here. If you want to analyze a system, what we do? In my last class, I told you that if you give an input impulse, you will get an impulse response. What is that impulse response? Impulse response is a signal, okay, which is specific to that system. Now, if you have to analyze the system domain, then what you do? You analyze the impulse response. So, again, what you are doing? By analyzing the signal, you are able to analyze the system quality, right? So, if there are unstable or even marginally stable systems where the unstable means when the signal is going out of bound, okay, where the output signal h and it is going out of bound, or marginally stable where the system response, it is not dying down to zero at time tending to infinity. Under that condition, Fourier transform, it fails to perform its duty. Okay, आया समझ में? शक्ल कुछ और बोल रहा है. पक्का आ गया? Okay. Anyone else? Clear? Okay. So now we know that there are certain disadvantages of the Fourier transform, and why these disadvantages are happening, that also we know. Now the next thing is why it is happening. Why it is happening? If you look into the operator of the Fourier transform, the operator is e to the power jw, j omega operator you can say, or omega operator. So we are only having frequency operator. Okay. So can it be overcome? Yes, it can be overcome. As I told you, Laplace transform, it is a generalized version of this thing. So in the generalized version, what you have, we have instead of e to the power j omega, we have e to the power st. So what is s? S is the Laplace operator, and it is given by S equals to sigma plus j omega. And when you replace this j omega with S, then the transform in the Fourier transform equation, then it becomes the bilateral Laplace transform. Okay, so let us see. Till now, I have not discussed any previous what you call uh, this derivations, but this derivation is important. So please look into this. So when we talk about the Fourier transform, what we have x of j omega, which is equal to capital F of xt. It is nothing but your Fourier transform of xt, and that is equal to integral of minus infinity to infinity x of t e to the power minus j omega t dt. This was our Fourier transform in this thing, right? And again, this is the inverse Fourier transform equation. Xt is equal to capital F inverse integral of the x of j omega, which is equal to 1 by 2 pi integral of minus infinity to infinity x of j omega multiplied by e to the power j omega t d omega. Okay. Now, say for example, I take a signal xt multiplied by e to the power sigma t, where sigma is real. So what is happening over here? What is this? E to the power minus sigma t. It is an exponentially decaying signal. So, right. So at t tending to infinity, our amplitude it would tend to 0. So if you multiply something with 0, even the exponentially growing exponential, if you multiply something with 0, it would come out to be 0. Okay. If you multiply infinity with 0, it would be 0. Okay. So you can see, just by multiplying with the factor e to the power minus sigma t, we have been able to make the signal bounded. We have been able to make the signal bounded. Now, since we have been able to make the signal bounded, now we can apply the Fourier transform and do the analysis. But this, so that is what we do over here. So see, Fourier transform of x of t multiplied by e to the minus sigma t. You see, I'm just writing this equation on the Fourier transform of this. Okay, x of t multiplied by e to the minus sigma t, which is equal to integral of minus infinity to infinity. See, x of t multiplied by e to the power minus sigma t. So only the xt is being changed into this form. Okay, e to the power minus j omega t dt integral of, which is equal to integral of minus infinity to infinity x of t. We are just taking this exponential and adding it up over here. So we get e to the power minus sigma plus j omega t dt. This is nothing but, just in few moments back I told you, it is a Laplace operator S. Okay. So we can say f of xt multiplied by e to the power minus sigma t, which is equal to x of sigma plus j omega. Okay. This is again the Fourier transform basically, but with a generalized version of your signal. Okay. Now, the IFT of the above equation, it can be represented in this fashion xt. Again the same thing over here. You take this equation, you change the xt to xt multiplied by e to the power minus sigma t and put it over here. Okay. Now if you see, there are some changes. We are going to the operator domain of S. However, there is no S over here. Okay. So in the next slide, let's see how to change the operator. We have this S equals to sigma plus j omega, which is the Laplace operator. Now you perform differentiation of over here. with d omega, ds by d omega, and like that. If you do it, you get d omega, then 1 by j into ds. Okay. So by applying this into this inverse transform equation, we get the inverse Laplace transform x of t is equal to 1 by j to pi integral of minus infinity to infinity x of s to the power st into ds. Okay. Whereas the Laplace transform, we change the value f of x of omega, xt into e to the power xt, sorry, xt into the e to the power minus j omega. This, if we replace it with x of s, so this is by changing that we get the Laplace transform and we get the inverse Laplace transform equation. Okay. Now, in our last class, we have discussed about the convolution sum. Okay. Now, the convolution sum, it was important where it was important for getting the output of a discrete time system or a digital system. Now, in Laplace transform, we have convolution integral. The same thing, but as I told you, this Laplace transform, it works for the continuous time signals. So we have, say, two signals, continuous time signals, f1t convolution of f2t integral of 0 to t f1 tau multiplied by f2 t minus tau d tau. And I hope all of you know why this t minus tau is coming. Over there we were having x of m into h of n minus n. The same thing. Okay. But if you see herein, what has happened? The limit, it has changed to 0 to t. Why it has changed to 0 to t? Because if you see, we have multiplied it with a to the power t, but it is multiplied with unit step function also. Okay, that means what is unit step functions? It starts at t equals to 0 and goes up to infinity. Okay, so the combination of this one, it is basically time limiting our signal component. Okay, it is time limiting our signal components. So due to this reason, if you see, the limit is 0 to t and not minus infinity to infinity. So this helps us in analyzing the output of a given system. Okay. So again, if you are having, say, LTI system xt, we have a system, so input signal, sorry, xt is the input signal, we have a system ht which is an LTI system. We get the output yt, which would be equals to xt convolution of h of t. Okay. Again, if you perform the Laplace transform, we get to xs. If you perform the Laplace transform of ht, we get h of s, and we get y of s, which is equal to h of s multiplied by h of s, and then if you apply inverse Laplace transform, we get to the yt. And again, if you want to come to the this Laplace domain, you apply the this Laplace transform to come to the ys. Okay. So rest of the process, if you see, it is remaining the same. Okay. Now coming to the Z transform. I told you that Z transform, it is used to solve difference equations. It is used to solve difference equations. Okay, difference equations are meant for the dt signals, discrete time signals. And I also told you that Z transform, it is a counterpart for the Laplace transform, which is used for the continuous time signal. Okay, so CT signals, they are represented with differential equation, whereas the difference equations represents the dt signals. We just talked. Okay. Now herein, the output of an LTI system, it is given by yn equals to hz into z to the power n. Okay. Yn is given by yn equals to hz into z to the power n, where hz, it is nothing but the Z transform of the impulse response. Okay, so if you see over here, hz equals to summation of n equals to minus infinity to infinity h of n, which is the impulse response, into z to the power minus n. Okay, now if you look into this equation, and if we generalize it for all type of signals, then what we get? We get x of z, it is equals to summation of n equals to minus infinity to infinity x of n to z of minus n. Why we have done? I have done because h of n, it is an impulse response, which is again a signal, right? And the transformation of that one into the z plane, it gives us hz. Okay, it gives us hz. Okay. So similarly, transformation of xn, it would give us x of z. Okay. So yes, Manibalan, thinking something? Okay. So this equation is the generalized equation of the Z transform equation. So it is a bilateral Z transform equation. Why bilateral? It is present both in the negative time domain and also in the positive time domain. So can anyone tell me the beauty of this equation? There is a beauty line in this equation. What is that beauty? Input output relationship for the transform. No, it is very easy to perform the Z transform if you are given with any type of signal. See, you are given with xn. Okay, say for example, you are given xn equals to 1, 2, 3, 4. What is the n? 0, 1, 2, 3. Done. If I have to find out the transform of this one, x of z equals to 1 multiplied by z to the power minus 0 plus 2 multiplied by z to the power minus 1 plus 3 into z to the power minus 2 plus 4 into z to the power minus 3. Just close your eyes and you will get to the complex domain pretty easily. So this is the beauty of the Z transform. Okay. Now we talked that when we are analyzing any biomedical signals, so biomedical signals, they are regarded as they are regarded as causal signals and systems, because for every cause there will be some signals. We consider that thing, right? This is why, because once you put on the sensor and start your machine, from that instance only you will be getting the reading. Previously, you will not get the reading. Okay, so we consider that all the biomedical signal processing systems, they are causal systems. Okay, so for that, if we change the limit this n from minus infinity to 0, so if the equation, if you see over here, if we place this, remove this infinity to 0, then we get the Z transform, which is regarded as unilateral Z transform. If it is, if the n is varying from minus infinity to infinity, it is called bilateral Z transform. On the other hand, if the n value changes to 0, then it becomes unilateral Z transform. Okay. So see, here we are given with. So what is the significance? As I told you, Z transform, it converts the sequence of numbers, which are the signals in the real domain, into an expression in the complex domain. Okay. The Z transform defined in the previous slide is defined as the bilateral Z transform. The unilateral Z transform of a DT signal is defined by this equation. The above equation notes or indicates that xn is equal to 0 for all values of n less than 0. Okay, for n less than 0. In other words, unilateral Z transform may be defined as a bilateral Z transform of xn, which is multiplied by un. Okay, x1z is useful to calculate the response of a causal system to a causal input. Okay, this is important. Now, we need to understand what is the relationship between the Z transform and the Laplace transform. Now, why you need to study this relationship? What is the need? As I told you that Laplace transform, it is analogous to the analysis of the um, analysis of the signals and the systems in the continuous time domain. So when did the digital systems it came into existence? Say 3 decades, 4 decades back, or 5 decades back. Previous to that, we were having the analog systems which were helping us. So the analog systems were more developed at that time, right? Now, when you start started to get into this digital domain, suppose you want to work on artificial intelligence or whatever in your research project. So what you will be doing? You will try to have or apply whatever the information you have from your previous experience, say from the lectures, what you are getting in the first year, or from your BTech, and then use those experiences to do your this research project. Obviously, while doing the research project, you will be interested in gaining more and more knowledge. Okay, so that you can refine your existing knowledge. The same thing happened over here also. When the digital signal processing it was being started, the analog or the continuous time signal processing it was quite developed. So what happened? the researchers were keen to develop the discrete time systems in such a way so that they can emulate the continuous time signal. Got my point? So they were taking the characteristics of the continuous time continuous time systems, and they were applying it to obtain a system which will be working for the discrete time systems, including the digital systems. Are you getting my point? So, due to this reason, later on you will see most of the filters and all these things what we try to design, we take an information from the continuous time systems, and then we try to design it for the discrete time or the digital systems. Okay. So, we have this x cap t which is given by summation of n equals to minus infinity to infinity x of nt multiplied by delta t minus nt. So this x, what is this? This x of x cap t, it is nothing but the sampled signal. It is nothing but the sampled signal. Say for example, you are having a signal. Now you are sampling this signal. You are sampling this signal with this delta term which we have discussed previously. Okay. So we have got this equation. Now let us apply the Laplace transform over here. So we get x of s, there should be a cap, sorry, x of s, which is equal to summation of n equals to infinity to infinity x of nt multiplied by e to the power minus n st. Okay. Now from our z transform, we see x of z is equal to summation of n equals to infinity x of n multiplied by z to the power minus n. So if you compare these two terms, rest of the terms they appear similar. So from here, what we said that this we have calculated for the discrete time, and we know that Z transform is already for the discrete time signals. Okay, so these two transforms should be comparable. Now, if these two transforms are comparable, then we can say Z is equal to e to the power st. You compare this part and this part because all the other parts are equal. So e to the power minus n st should be equals to z to the power minus n. Okay. So z equals to e to the power st. Right. Now, but s is equal to sigma plus j omega. So we say get z equals to e to the power sigma plus j omega t. So just break this one into e to the power sigma t. You get the real component and the complex component. It comes out to be e to the power j omega t. Okay. So modulus of z, it is always the real term, e to the power sigma t, and phase angle is omega t. Okay. Now when sigma is equal to 0, this whole term it becomes 1, modulus of 1. But we know that z equals to e to the power omega t, and if you break it down, you get this thing. So how do you get 1? Basically we are trying to get the modulus, and that is nothing equal to under root of cos square omega t plus yeah, sine square omega t. Okay. So what is this? This is nothing but the equation for a circle having a radius of 1. So z plane is nothing but, you see this carefully because many students they do mistake. So in the z plane we are having a real z, we are having an imaginary z, and we are having one unit circle. Unit circle means a circle which is having a radius of 1. Okay. Now, if you compare over here with the Laplace domain, in the Laplace domain we are having real component, sigma, and y-axis was j omega, j omega. So what? When we got this unit circle, we got the unit circle when sigma is equal to 0. When the sigma is equal to 0, when it is on the j omega. Okay. So when we are mapping the Laplace transform to the Z transform, what is happening? This frequency axis, it is being mapped onto the unit circle. Where is the frequency axis of the Z plane? Frequency axis of the Z plane is onto the unit circle. Okay. Many students they do mistake. Many of you, not many, all of you will be going for the comprehensive exam for the year before you pass the MTech degree. So many students they tell, when I ask them the Z plane, discuss about the characteristics of the Z plane, they answer that it is a three-dimensional space x, y, and z. This should be incorrect. Z plane, it is a 2D system. That's why I am giving a stress over here. This will form the basics of yours. Okay. So Z plane, it is a 2D plane. It is not a 3D plane. Okay. It is a 2D plane, and we are having a unit circle. That unit circle is the frequency component. Now over here, if you see the frequency component in the Laplace transform, it can vary from minus infinity to infinity. However, if you see in the Z plane, it starts with 0 from here, and then it goes and it comes to the pi, 2 pi. First pi it would come, and then it would come to 2 pi. So what would happen to rest of the frequency components? So as you go on increasing the frequency components, they will be overlapping on the same points. So this is called many to one mapping. Many frequencies, they are getting mapped into a single frequency. That is why the band limiting, it is important. You need to do the band limiting so that this many to one mapping can be stopped. Again, I talked about the Nyquist criteria, where I told you your sampling frequency should be greater than equal to 2 of Fm. What is the maximum frequency over here? The maximum frequency over here is 2 pi. So 0 and sampling frequency, they will be coinciding at this point where you have the DC frequency. And where will be your Fm? Considering the Fs equal to 2m critical frequency, so it should be at 5, right? However, I also told you that mm, when you are going for this thing, say low cost data acquisition system, 2 of FM, it may not be sufficient. You may be interested in going to Fs equals to 3 of FM. So what happens for the 3 of FM? So what would happen? So your Fs is here, say it is 200. In the first case, pi would have been having 100 frequency, okay, 100 hertz frequency. Now when you are talking about this Fs equals to 3 of Fm, okay, so your frequency remains the same. So 200 by 3, 66.66. So it should be somewhere over here, right? So what is happening? You cannot go beyond that. Okay. So all these frequency components, they will be compressed over here. So this is called frequency compression. So if you go for higher sampling frequency, you will be left with smaller and smaller area to work on to design the filter. Okay, because anyway you cannot go beyond pi. So you cannot go beyond pi, so you cannot go over there. But if you increase the sampling frequency, you will be pushed towards the DC frequency, and you will be left with very small number of small area to design your filter. So you will be losing the frequency resolution of your filter. Okay. Now if your sigma is less than 0, it maps into the unit circle, within the unit circle. If it is greater than 0, then it is outside this unit circle. Okay. So this is how Laplace transform plane, or the S plane, it maps into Z plane. Okay. Now what is the relationship between the Fourier transform and the Z transform? So this is your Z transform we have just discussed, and we have Z, which is equal to R into e to the power j omega. So if you put it over here in this equation, we get x of r into e to the power j omega, which is equal to summation of n equals to minus infinity to infinity x of n multiplied by r of e to the power j omega to the power minus n. Okay. Now you break this and bring these real components together and the non-real over here separately. So what you get, f of xn multiplied by r to the power minus n. When r is equal to 1, when value of r it is equal to 1, so we get x of e to the power j omega, which is equal to f of xn. What is this? This is nothing but when your radius is 1 of the z plane, when your radius is 1, we are basically onto the Fourier transform axis. Okay. So what is the Fourier transform axis? It only contains the frequency component. So just now whatever I told you, this unit circle, it is the frequency axis, not the real z, not the imaginary z. Whenever you'll be going for designing anything, so these are the basic things which people ask. Okay. Even students who come for the PhD and have done uh, what you call PhD on say adaptive filtering and all these things, they I have found they don't have their concepts clear. Okay. So in interview, whatever interview you go, they would ask you for the basics. So that's why I am stressing on the basics. Okay. So in Z plane you are having real Z, imaginary Z, and frequency axis is the unit circle. Okay. Keep this in mind. With this we complete this chapter. If you have any questions, so you can discuss.